We know that walking across a row is better than going down a column, but is that the actual best thing we can do? So here we have our good case again. We're varying j, so that means we're walking across the rows b and c. But let's imagine what happens after this iteration when we go around to the next iteration on the I loop. Right? That is I increment. So we go down one spot in j, we go down one row in c as well. But b, since it doesn't depend on I, is going to be looking at the same data that it looked at before. And if the row is so big that it doesn't fit in cache, then by the time we walk to the end of the row for the red iteration, then on the blue iteration, we're going to walk back over the same data, but it's been flushed from the cache, and so we'll get exactly the same misses that we got before. Right? That was the misses that we computed that we expect. It's going to be a 25% miss rate. But it seems a shame, and in particular, we're walking across red and then blue and C. If we did just enough red to get a cache effect, right, to make maximal use of the cache block that we pulled in, and then if we did a little bit of blue, right, we would be pulling in new cache lines just as if we continued on red. But if we do it that way, then we're going through a little bit of B and then through the same part of B, and we will get less than a 25% cache miss. So that's the basic idea. We want to make some compromise between walking across the row and walking all the way across the row, when we could do just as well by going down a column over here and do better by staying in a little fragment of the row over here. So that's the idea. And that idea is called blocking. So what we're going to do, this is the same picture that we had before, but instead of just being one row across, these are squares that are some number of rows deep and the same number of columns across. Right? In fact, we'll call that number W. This is W by W chunks. And the way we compute matrix multiplication is we take this chunk and matrix multiply it against this chunk and put that there. And then we have this chunk, the second block in A, against the second block in B, and add it on top of the one that we had there. And we can do all the blocks across of A and down to B to get the same result that we got before. In code, it looks like this. We have our big ijk on the outside, but this I is going to increment by W. That is, when we get to the next I, we're going to go W rows down instead of just one row down. Meanwhile, within each ijk chunk, we have iijjkk that's going across W elements of our array. Right. So the code is more complicated. We have 6 nested loops instead of 3 nested loops, but it's not so outrageous. And the question is, what is the performance of this in terms of cache misses? So if we pick a W, we're going to remember our motivation from before is pick a W that's wide enough. Pick a chunk of an array that's wide enough to let us get the good cache effects while also continuing down in B. Then we could just pick a W that's small enough so that W squared elements fit into the cache, because we're going to be, it's really 3 times W squared elements, working on this block with this block to contribute to this block. So as long as we keep all, if we can fit all 3 of those into the cache, then it doesn't matter what order we do things, even if we're going down and across within those blocks. So that's what we're going to do. We're going to pick small enough W so that the elements fit in the cache, so we're going to get that optimal 25% miss rate. So each of these red boxes is W squared elements. How many of them do we have for each iteration of these chunks here? Well, we have n is the whole width of this array, so it's n divided by W blocks, right? And we have 2 of those kinds of things. We have n divided by W of them over here, so that's 2 times n divided by W times each block is W squared elements. And then we have the one in C also, if we want to count that one, which is another W squared. So what we're saying is, because that fits in the cache, we're going to get a 25% miss rate from those elements. We're going to repeat all of this n divided by W squared times, right? Because we're getting this block in C, and then this one, and this one, and then this one, and this one, right? We have n divided by W this way, and n divided by W this way. That many copies of this. Well, if n divided by w is a reasonable number of blocks, then this will be much bigger. This 2 times n divided by w term will be much bigger than this one. So we'll ignore this one. What we have is this times 0.25 misses. And if we multiply that all together, then that's n cubed divided by 2w. Which means that it's 1 over 2w times n cubed. N cubed is the number of operations we have. So we have 1 divided by 2w misses per times through that loop. And if w is at least 2, that's better than 25%, or that is 25%. But if w is more than 2, then it's better than 25%. So blocking is a way that we can further increase temporal and spatial locality, especially temporal locality, because we're staying in a particular row for a while before we move on, all based on picking a suitable block size. Right? We want to make it big enough to get the biggest reduction in the miss rate, but small enough that everything still fits in the cache when we have just 3 of the blocks.